Now we will find the Fourier expansion of fx is equal to x square. So Fourier expansion will be f of x is equal to a naught plus summation of n is equal to 1 to infinity an cos nx dx. So now first we will find out a naught. The formula for a naught is 1 upon 2 pi integration of c to c plus 2 pi f of x dx. So this is the general formula. We will put the value in this. So it will become 1 upon 2 pi minus pi to pi f of x is x square dx. Now when we multiply it by 2, then it will become 2 upon 2 pi 0 to pi x square dx. And integration for x square is, first this 2 will get cancelled and it will be 1 upon pi. Integration of x square is x raised to 3 upon 3 0 to pi. This 3 will come out and it will become 3 upon pi, sorry 1 upon 3 pi x upon 3 0 to pi. Now when we put the value in it, this will become 3 upon pi raised to 3 minus 0. So this pi and this pi will get cancelled and it will be pi upon square upon 3. So this is the value of a naught. Now we will find out an. So formula for an is 1 upon pi integration of c plus 2 pi c f of x cos nx dx. So it will become 1 upon pi integration minus pi to pi f of x is x square cos nx dx. So u into v rule will be applied. This sin x and this will be get cancelled. This x and this x will be cancelled. When we apply limit on it, it will become 2 into 2 upon pi cos n pi upon n square minus 0. Then it will become 4 pi and value we know that cos n pi is minus 1 and this is the pi n square. This pi will get cancelled and it will become minus 4 upon n square. So this is the value of our an. So Fourier expansion is fx is equal to the value of a naught plus put the value in it. The value of a naught is pi square upon 3 summation n is equal to 1 to infinity. Value of a naught is minus 4 raised to n square cos n. So this is the Fourier expansion for given function.
1.
In previous session, we already see the Fourier series for even function. Now we see the Fourier series for the odd function. So this is our question. Find the Fourier series for x cube from pi to pi, minus pi to pi. So here f of x is equals to x cube. Put minus x in x. So therefore f of minus x is equals to minus x of cube. So here is f of x is not equal to f of minus x, as you can see here. So therefore it is odd function. As we know that for odd function we see the series like this. We only find the Bn, and here an is equals to 0 and a naught is also equals to 0. So therefore Bn is equals to 1 upon pi minus pi to pi f of x into sin nx dx. So for our simplification, we will put here definite integration, as we know that f of x is equals to minus a to a f of x dx. We also put limit like this 0 to a f of x dx for our simplification. So I put this limit here. Bn is equals to 2 upon pi, because here is a multiply factor is 2. So I take 2, then our limit is 0 to a. Here I put here 0 to pi. F of x is our x cube and sin nx dx as it is. Now Bn is equals to 2 upon pi. So here is a u into 3. U is our x cube and v is our sin nx. We take derivative of x cube and integration of sin nx. So first term is add as it is, that is x cube, and the integration of sin nx is cos nx upon derivative of nx is n. So then we will take minus sign, then the derivative of x cube is 3x square, then integration of cos nx is sin nx. Here is a minus sign, so we take minus sign and we write this n, and here is already one n, so it is n square. Also here is a minus, so we take the plus, then the derivative of 3x square is 6x, and integration of this whole term is cos of n x upon n cube. Here is already minus sign, and cos also having minus sign, so minus minus get plus, and there is the integration derivative of 6x is 6, and cos of nx is minus sin of nx upon n raised to 4, and our limit is from 0 to pi. As you can see here, as we know that if we put here pi or 0, it will become 0. So this sign term and this sign term will be cancelled. Now, so what is remaining here? 2 upon pi x cube into minus cos of nx upon n, here plus 6x into cos of nx upon n cube, and our limit is from 0 to pi. cube into minus cos of n pi upon n plus 6 pi into cos of n pi upon n cube. And if we put here 0, cos 0 is 1, but here is x, 6 is with x, so if we put here 0, then it is automatically become 0, so minus 0. Now Bn is equals to 2 upon pi. Here is a pi cube and 6 pi, so pi 1 pi will be common from them. Then here is a pi square into minus 1 upon n plus here is a 6 upon n cube, and cos n pi will be common from here. Now Bn is equals to this pi will be cancel out, so here only 2 is remaining, so here is a pi square minus pi square upon n plus 6 upon n cube. But as we know that here is a cos n pi, if there is a n is a even number, so we will take 1, and if there is a odd, we will take minus 1, but we don't know what is it, so we will take the formula of minus 1 raised to n. So therefore Bn is equal to 2 into minus 1 raised to n into minus pi square upon n plus 6 upon n cube. So this is our Bn. So now we put this value in our Fourier series. So for Bn, Fourier series is equals to summation of n equals to 1 to infinity Bn into sine of nx dx. So what is our function? First of all, our function is x cube. So therefore x cube is equals to summation of n is equals to 1 to infinity. What is our Bn? Bn is 2 into minus 1 raised to n. So I put this value here into minus pi square upon n plus 6 upon n cube into sin nx as it is. So this is our Fourier series, final Fourier series for Bn or for odd function.
Hello everyone, my name is Vivek Sate and my roll number is 64, and the topic that I am going to present today is complex form of Fourier series. So before getting started, let's recall that the real sine and the cosine form of the complex well is given by e raised to exponential function e raised to minus inx minus e raised to minus inx upon twice I, and that of cosine is given as e raised to inx plus e raised to minus inx upon 2. So these are the functions of the sine and the cosine that are given by the complex form. So after that, when we substitute this sine and cosine in the complex form, we get the Fourier series of f of x is equal to c naught plus c1 into e raised to inx plus c suffix 1 into e raised to minus inx plus c2 into e raised to twice inx plus c suffix minus 2 into e raised to minus twice inx. So these are after substitution we get the Fourier series of the complex form like in this form. So after the real and the cosines are substituted, the complex form of the Fourier series can be given by this term. So these are the sine and the cosine of the complex form that can be expressed in the exponential functions, where we are given the terms of the exponential function, that is formulas. So after substituting these values, we can get the complex form of Fourier series by the exponential functions of it. So it goes as c0 plus c1 into e raised to inx plus c into suffix minus 1 into e raised to minus inx plus c2 into e raised to twice inx plus c suffix minus 2 into minus twice inx. So with the coefficient we can be given as therefore c0 is equal to 1 over twice pi integration minus pi to pi f of x dx. This is the standard form of the complex form of serial series that will be given as the function and its derivatives and integrals. So after substituting it in the function, it can be given as 1 upon 2 pi integration minus pi to pi f of x. After the standard form, it can be given in the complex form of the Fourier series, that is e raised to minus I n x dx. After giving the functions of the complex form of Fourier series, let's just try to go in the even or odd function. So for the even function, if the let's take out the even function of the interval minus pi to pi. So the even function of the interval can be given by is given when the interval of minus pi to pi is given by 1 upon 2 pi pi integration minus pi to pi f of x dx. So after substituting, we can get its forward 2 upon 2 pi pi integration minus pi to pi f of x dx. So after solving this, we can get a naught by 1 upon pi integration. The limits can be exchanged with 0 to pi, so it goes for f of x dx. So after giving the complex form of Fourier series and its even function, so let's go into the solving by the a naught. So how to determine if the cos n x and sin n x are even in the function or not? So for cos n x, f of x is equal to 1 upon pi integration minus pi to pi f of x into cos nx dx. So after substituting its intervals, it can be written as 2 of pi integration 0 to pi f of x into cos nx dx. So it can be seen that this function is also for the even function, and it can be written as therefore f of x of cos nx is an even function. So after finding the a naught, let's just try to go for the bn. That can be given as bn is equal to f of x is equal to 1 upon pi into integration minus pi to pi f of x into sin nx dx. So it can be directly seen that this function is already the odd function, so it can be written by f of x of sin nx is an odd function. So that was all about my presentation for the complex form of Fourier series and also for the even function.
My name is Vaibhav Kasa, roll number 65. So I will take the example on complex form of Fourier series. So example is obtain complex form of Fourier series for f of x is equal to e raised to minus x in limit minus pi to pi. So where a is not an integer, so our solution is f of x is equal to e raised to ax. So for solving this example, our main formula is f of x is equal to summation of n is equal to minus infinity to infinity Cn e raised to minus I n x dx. It is the main formula for solving this example. So for I will find the Cn. So for finding the Cn, the formula is 1 upon 2 pi integration minus pi to pi f of x e raised to minus R n x dx. So our f of x is 1 upon 2 pi integration minus pi to pi e raised to ax into e raised to minus R x dx. So limit is minus pi to pi. Then we put the limit. So 1 upon 2 pi a minus I n. So limit. First we will put the upper limit. So e raised to pi a minus in minus lower limit e raised to minus pi a minus in. So we multiply this e raised to pi over a
How to do it?
minus in. So 1 upon 2 pi a minus in. So e raised to pi a into e raised to minus in pi minus e raised to minus pi a into e raised to minus n pi. So we know the e raised to minus in pi is equal to minus 1 raised to n. So put this in the 1 upon 2 pi a minus in. So e raised to pi a, we put this minus 1 here, minus e raised to minus pi a into minus 1. So I will take this minus 1 raised to n power minus 1 raised to n upon 2 pi a minus n. So remaining is 1 raised to pi a minus raised to minus pi a. So we multiply this to the divide side. So minus 1 divided by pi a minus pi e raised to pi. So bracket here. So we know the formula of sin hyperbolic. X is sin hyperbolic x is equal to e raised to x minus e raised to minus x upon 2. Using this formula, we convert into the sin hyperbolic pi. So minus 1 n into sin hyperbolic pi. By mistake, there is a or minus. So here a pi upon pi into a minus r here. So using the complementary dividend rule, minus 1 n sin hyperbolic a pi upon pi a minus r n multiplied by a plus in upon a plus in. Multiply this sin hyperbolic a pi into a plus divided by this a minus in and a plus in is a square minus in square. So pi into a square minus in square. We know the, so here I did because numerator terms is like this into a plus in divided by pi into a square. So here is the minus 1 square. 1 square is equal to minus 1. So put this in this I minus 1. So this minus 1 and this minus is plus 1. So here remaining is a square. Here is the solution of Cn. So solution of Cn is here. So